Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar lecture theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar.
Friends, in this lecture, we are going to discuss in more detail about temperature calculations. So we have seen how when we want to consider effects of fire on structures, the calculation of structural temperatures is a key aspect of that. And we have also seen this one-dimensional heat conduction equation where this rho and C, these are material properties, rho is for density and C is for specific heat and K is another material parameter which is thermal conductivity. If you recall, K was the proportionality constant which arisen from Fourier's law of heat conduction, okay, which simply states that the heat flux in conduction is directly proportional to the temperature gradient, which is derivative of T in the x. Now when there is one more term here which is S, which stands for a heat source term, which means in case there is a production of heat or loss of heat within the domain, that can be catered through this parameter. But for the structural fire applications, since there is no heat production or loss within the structural member, the S is generally 0. The other thing is that the parameter K or thermal conductivity, it is generally not a function of space, which means K remains the same throughout the structural member. So if it is a steel beam, conductivity of the steel beam will be the same regardless of the location where we are located in. Okay. In such a case, this K can come outside of this derivative, and we get a more simplified term to work with, which is K times second derivative of T with respect to X. Now in this case, T or temperature is a function of both X, which is the space variable, and T, which is a time variable. Okay. So if we consider a domain here, which is shown here, say this is X equal to 0, and this is X equals to L. So this is the overall length of the domain where we are interested in the temperature distribution. At any point X, okay, the temperature will be a function of space variable X and time variable T. And this is the domain between X equal to 0 to L, where we want to solve this transient heat conduction equation, which is rho C derivative of temperature with respect to time is equal to K times second derivative of temperature with respect to space. So when we solve this equation, we will get the temperature distribution throughout this bar or the domain, 1D domain, as a function of both X and T. Since this has two boundaries at the two ends, we require two boundary conditions. And since there is a time dependence also, we need one initial condition. Initial condition simply means the initial temperature distribution of the domain, or in this case we have been calling it a bar. Okay. The boundary conditions we have already discussed previously. We can have boundary conditions where temperature is fixed or given. Okay. We can have boundary conditions where we have flux given, or we can have Robin type boundary conditions where the convective radiative conditions which actually arise in fire analysis, they can be applied. So to be able to solve this differential equation, here we have used another parameter called alpha, which is called thermal diffusivity. So this parameter is a ratio of the conductivity to the rho times C. And since we have assumed that material properties do not vary with x, this alpha can be also taken out of the second derivative and can be written in this way. Now, it is possible to solve this equation analytically for a certain simple cases. However, when the boundary conditions become complicated, which is the case especially for fire scenarios, or when alpha or the material properties become functions of temperature, in that case this equation becomes nonlinear and analytical solutions become increasingly difficult to obtain. This is where a very simple numerical method called finite difference method can be used to solve such equation. Finite difference method you may have already learnt during your engineering degree curriculum. It simply works by approximating the derivative. So let's say we want to calculate the first derivative, it simply says this is delta y by delta x, okay, or in other words yi plus 1 minus yi divided by x I plus 1 minus xi. Now what is this xi yi? So we again go back to the domain as shown here. So this is the first point. Let's call this x0. Okay. We subdivide this domain into multiple points. We choose points along this domain. Okay. And each point we call x1, x2, x3, like that. So there is xi minus 1, xi, xi plus 1, and then finally there is x end, or the last point. Okay. So what we want to be able to solve this equation is these two derivatives approximated using this type of a method throughout the domain. So for time derivative, a very common finite difference scheme which is used is shown here, where this superscript n shows the time at which we are at. Okay. So which means this n implies that we are at a time step n. So just like we are dividing this space into multiple chunks, similarly if we want to start from t naught to t end, the total simulation time, in between we will have a time step of delta t, okay, and each subsequent time position is termed as tn. So the time derivative of t at nth time step at ith space location, which means at x equal to I, can be approximated as this t n plus 1 minus t n divided by delta t. So a similar sort of concept that we have introduced here, and this scheme is called the forward difference. Forward difference because we are using the future time step first and then calculating this. Okay. And for the second derivative of temperature with respect to space, so we are approximating this derivative at node I, which is again here, for time step n. Okay. So that takes this form, and this can be derived using a central difference scheme. Now, central differencing is generally a preferred way of doing finite differences. However, for single derivatives, it leads to half nodes, and that is where in general for double derivatives it comes out with more simpler to use expressions, and for time we have used forward difference. So now we take this derivative and substitute it in the equation, and we take this derivative and again substitute it in the equation. What we get is left hand side is the time derivative, which is coming from here. Okay. This is equal to alpha times the space derivative, which is coming from here, right. So from here we can write an expression for t I n plus 1, which is the next time step or the future time step, in terms of the known temperature of the current time step plus this term. And it is usually common to define the Fourier number, which is defined as alpha times delta t over delta x square. Okay. So it appears here. So alpha times delta t over delta x square appears here. So we can rewrite the expression for t I n plus 1 in terms of the Fourier number in this manner. Okay. Now the way we have used finite difference method here, this is an explicit finite difference. This is an explicit scheme. Okay. And explicit schemes are generally conditionally stable. And what I mean by conditionally stable is that this delta t and delta x, they need to be defined in a certain ratio that so that the numerical scheme converges. Okay. So otherwise, so let's say we are trying to solve a problem for a large amount of time, long time. It may be tempting to use a large value of delta t so that we can take larger time steps. Okay. But if you are using an explicit scheme, using larger time steps can render the numerical scheme unstable, which means whatever solutions we get from there, they will not be accurate. So for this particular scheme that we have used here, the Fourier number must be less than or equal to 0.5, okay, which implies that this alpha times delta t over delta x squared is less than 1 by 2, less than or equal to. So which means delta t must be less than or equal to delta x squared divided by 2 alpha. Okay. So once we have chosen the discretization in space, which means we have chosen our delta x, then we can calculate what is the largest time step that can be taken for that particular delta x, so that this scheme remains stable. If we choose a larger time step than that, then this will not be stable, and the numerical results that we obtain will not be accurate. And as I mentioned earlier, we need to give boundary conditions, okay, which means the two ends of the bar which are here and here, that is where boundary conditions are required. And we've already seen earlier that boundary conditions can be of three types. One is the Dirichlet, where temperature is given. Then one is Neumann, where flux is given. And the third type is Robin, which is a mixed boundary condition. And this is typically used for convection and radiation exposure, which happens during real fire scenarios. Let's look at it from an example point of view. So we have a 1 meter copper bar where the thermal diffusivity is given. The bar is initially at 20 degrees Celsius, which means the initial temperature is 20 degrees Celsius. Left end is held at a temperature of 20 degrees. So let us show that. So here we know that temperature is 20 degrees Celsius. So because temperature is given, it is a Dirichlet condition, and right end temperature is suddenly increased and maintained at 100 degrees Celsius. Okay, so this is also a Dirichlet condition, and we know that the initial temperature is 20 degrees Celsius. Okay, so now if this now we have to determine the temperature profile of the bar with time. So let us say we divide this in, we have two end nodes and we choose two more nodes in the middle. So let's say this is at x equal to 1 by 3, this is at x equal to 2 by 3, this is x equal to 1, x equal to 0. Now the expressions for derivatives and time schemes we have already written. Okay. So in this case delta x is 1 by 3, which means delta t should be less than or equal to delta x squared divided by 2 alpha. So this is delta x squared is 1 by 9, then we have 1 by 2, and then we have 1 by alpha, which is 1.11 times 10 to the power minus 4. Okay, so this alpha is in meter square per second. This 1 by 9 is in meter squared. Okay, so eventually we will get delta t in terms of seconds. Okay. So if we calculate this, what do we get? So we get 1 divided by 9 times 2 times 1.11 into 10 to the power of minus 4. Okay, so this comes out to be 500 seconds. So this is the delta t which can be used. Now we can go to our time stepping scheme, where we say, now we know that t at all the nodes I at 0th time step, this is 20 degrees Celsius. Okay, this is the initial condition. Now in terms of node numbers, we can say this is I equal to 0, I equal to 1, I equal to 2, I equal to 3. So what we also know from boundary conditions is that T0 for any time step is going to be 20 degrees Celsius. Okay, this is boundary condition. and T3 at any time step is going to be 100 degrees Celsius, right? So now we can write, so we have 0, 1, 2, 3, this is the I values. Okay, so we can write now T1 from here, T1 at the next time step, which is the future time step. This is 1 minus 2 times Fourier number multiplied by T1 at 0. So here we have the previous time step plus Fourier number times Ti plus 1, which means T2 at 0 minus Ti minus 1. Ti minus 1 for 1 will be T0 at 0. Okay, and the Fourier number also we can calculate from here. So Fourier number is given here, alpha delta t divided by x squared. Okay, so this you can calculate. So Fourier number can be calculated. Now T10, this is temperature at node 1 at the initial or the previous time step. This is 20 degrees Celsius. This is coming from the initial condition. T2 at 0 is also coming from the initial condition, and this is also coming from the initial condition. Okay, so we will see that the second term becomes 0 because both are 20 degrees as of now, and this can be obtained as 1 minus 2 times Fourier number multiplied by 20 degrees Celsius. And similarly, we can write an expression for T1 at the second time step. Okay, so again this will be 1 minus 2 times Fourier number T1 at 1, the first time step, the previous one which we have just calculated, plus Fourier number times T2 at 1 minus T0 at 1. Okay, so now let's look at the numbers here. Fourier number will remain the same as previous one. This T1 has been calculated in the previous time step, so that will come here. T2 will also have been calculated from the previous time step, similar to the T1, so that comes from there. Now T0, which is temperature here, this still remains 20 degrees Celsius because this is a boundary condition. Okay, so this is how we can proceed with this type of calculations. This is again a quick recap of the boundary conditions. So when the temperature is given, it's a Dirichlet condition. This is what we had in the problem that we just solved, which means T, an example is that T at x equal to 0, which is one of the ends, for all times is this, and this can be a function of temperature also, a function of time also. Then there is a Neumann condition, which is heat flux given, okay, like this. And then Robin condition, which is the most commonly used condition in case of fire, where this first one is a convection condition, where Tg is the gas temperature and Ts is the surface temperature or the boundary condition temperature that we want to establish. Now notice here that Ts will be an unknown, so this has to be solved along with the main problem. Similarly, this is a radiation condition, where Tg again is the gas temperature and Ts is again unknown. Okay, these are properties which will be known. Now this third one is a combined convection and radiation condition. Okay, if both the effects are acting, then this is how we can apply that boundary condition. So this is about being able to calculate temperatures for any general sort of material and for any general sort of condition. What we have seen here is a one-dimensional heat equation, but similar practice can be applied to a two-dimensional heat equation in case it is necessary. All right. So instead of a single dimension, we will have then two dimensions. Instead of solving along a bar or a line like this, we will be solving along, say, a rectangle. Okay. And again, we will require some boundary conditions and some initial conditions, a full initial condition for the plate. Now, there are materials from a structural point of view, steel being one of the most common materials apart from concrete. So, steel is a conductive material. Conductive means it is a good conductor of heat. Okay. So, for materials which are conductive in nature, we can assume that if we are heating it at one end, the entire body has the same temperature. Okay. Now, this is an assumption. However, from a design point of view, this is a conservative assumption. Okay. Because what we are assuming is that conduction has become instantaneous, whereas in reality it is not. So, it will take some time for the material to reach that particular temperature, whereas we are assuming that the entire material has reached the same temperature instantaneously. So, we will be overestimating the temperatures in this case. Okay. So, from a design point of view, it is okay. But the advantage it gives us is that the calculations becomes very simple as compared to the previous finite difference method that we have seen. We are able to obtain even closed form solutions in certain cases. Now, since the heat capacity of the entire volume of the material is now been lumped to a single point, that is why this is called a lumped capacity model. Okay. So, in the previous example, the dimensionality of the problem in space was single, which means it was a one-dimension problem. Now, the entire volume has been lumped into a single point. So, this becomes a zero-dimensional problem. Okay. So, this is single point, which means zero dimension. So, basically we will be able to solve without worrying about the space derivative part. Okay. So, the overall governing equation can be simply obtained by energy balance, which is the heat received is equal to heat stored. Okay. There can also be a term of heat leaving out in case that term is there. So, heat received is simply the rate of heat received multiplied by the dt, which is the time of exposure, and the stored heat will be simply the volume times the volumetric capacity. If you recall, this specific heat is the storage capacity per unit volume, per unit mass. Rho is the density. So, when we multiply all of that with volume, we get a volumetric capacity per unit temperature, and then delta T is the change in temperature. Okay. So, when we equate this, we get the governing equation like this. So, the time derivative of temperature is equal to A divided by rho Cv times Q dot. Q dot is the incident heat flux on the system. Okay. And we notice that now the derivative in space has been lost, primarily because we have now assumed it to be a zero-dimensional problem. Okay. And for thin plates, there is a term called section factor, which is commonly seen in several building codes, which is defined as this ratio of A over V. So, basically then we use that. So, we can write this A over rho Cv simply as d by rho C times Q dot dash. So, now we have only time derivative. So, the finite difference solution will involve only the time term. Okay. So, we are approximating the time derivative just like we did earlier using forward difference. Which is that dt divided by d small t, t is temperature, capital T is temperature, small t is time, is approximately equal to t at n plus 1 time step minus t at n divided by delta t. Okay. So, in this case, this temperature will be only a function of time. Okay. So, let us say the variation is like this. What we are doing here is that we have, say, T1, T2, these are the times at which we are calculating, T3 and so on. The interval between these two is what is delta T, and temperature here is T1 temperature here is T2, temperature here is T3, like that. Okay. So we are approximating in between as a straight line. That is what gives rise to this type of a expression. Okay. So we are again using forward difference here. So when we put all of this together, we obtain an expression for delta Tn, which is the rise in temperature. Okay. And from there we can write this Tn plus 1 as Tn plus delta T d divided by rho C n Q n. Okay. Now what we will notice here is that this C, or the specific heat, we are admitting as a function of time, or in other words temperature. So it is possible to change it at each time step, and we will see why that is required shortly. Okay. Tn is the previous time step which is known. When n is equal to 0, Tn will be known from the initial condition, and then it all gets calculated subsequently. And here also for delta T there is a limit, so the delta T max is this for stability, otherwise numerical instability issues will arise. Okay. But from a practical point of view, generally delta T that should be used should be about not more than 5 to 10% of delta T max, which comes from here. Let us look at an example where we use this lumped capacity model for aluminum. So there is an unprotected aluminum section, okay, with a section factor which is given. Section factor is A by V, which is 1 by 70 meter inverse. It is initially at room temperature, so this is the initial condition, and it is suddenly exposed to a constant fire temperature of 350 degrees. Okay, so we have not yet brought in the change of temperature with time. We are saying initially it was at 25 degrees Celsius, now it is at 350 degrees Celsius. So calculate its temperature as a function of time. So we want to see how, what is the rate of change and things like that, right? Now what we are given is aluminum emissivity is given, and the convective heat transfer coefficient is also given. Okay, so we can write a simple code, and the code I am showing here has been written in MATLAB, but you can use any other programming language of your choice. And our objective here is to understand the logic of writing this code so that you can write your own codes wherever required. So this is the given data. Okay, Ti is the initial temperature. Notice that we are converting all the temperatures to Kelvin because we will have to use radiation. Okay, and radiation relations require temperatures to be in Kelvin. Now this is all the assumed or found data. Okay, then we define some data structures to hold. So we are calculating from 0 to the maximum time, which was 3600 seconds, and dt is the time step that we are using. Okay. So we are using a time step of 10 seconds. So so we have a bar like this where we are saying the first temperature T1, okay, this is the initial temperature, and on the other end we have the Robin boundary condition which is applied. Okay, so which means flux is Hc times delta T. Okay, this is the convection boundary condition, and this is the radiation boundary condition. Okay, this coefficient is nothing but delta T times d divided by rho C, which is this term here. Okay, so basically we can calculate Tn plus 1 as Tn plus this coefficient multiplied to the flux, and flux we are calculating here. Now, since we are using a lumped capacity model, this entire length is lumped into 1. Okay, so T1 specifies the initial temperature or the initial condition, and subsequently T2 and T3, etc. These are the future time steps. So to calculate those future time steps, we have written a for loop here. Okay, so we go all the way to n minus 1 because we are calculating I plus 1, which is the next time step. Okay, so Ti plus 1 is Ti plus Q coefficient. This coefficient remains constant because as of now we have not considered any time variation of C. Okay, so the coefficient multiplied by Qi, which is the flux, but flux will get updated at every time step. Okay, because it depends on the temperature, right? If you recall the TS is an unknown, it is not known a priori. But once we go through this for loop, we would have calculated temperature at all the time steps. Okay, so again if we say T versus small t, we start at an initial condition, then we go to the next one, we go to the next one, like that, up to the time T max, which is the desired time of duration. Finally, we just plot. So let's look at these plots. So when we run the code, we generate a graph between temperature versus time of that steel bar, okay, assuming a lumped capacity. So it starts at 25 degrees Celsius, which is the initial condition T naught, and then it gradually increases and eventually it becomes same as the surrounding temperature. Okay, this is what is expected also. And similarly, this heat flux can be drawn. We looked at one idealization where if a material is conductive, we can assume that the entire material is at the same temperature. Okay, that is a lumped capacity approximation. The other approximation we can use is for insulating materials. Okay, the idealization is called semi-infinite idealization. So if we again consider a one-dimensional domain here, okay, now we are out of the zero-dimensional domain. Let's say that initially the entire bar is at a temperature of T naught. This is the initial temperature. And then on this end, the temperature becomes Ts. Okay, we suddenly raise the temperature, which means here the temperature is higher, which is Ts. What the semi-infinite idealization states is that because this particular material is not very conductive, if we are sufficiently far away from the location of the high temperature, let's say if we are at this end, which means we are at x tending to infinity mathematically, but say sufficiently far off, then the temperature remains initial temperature. The temperature would not have risen because of poor conduction. Okay, so the graph of temperature with space will be like this, which means that up to a certain distance the effect of Ts is felt, but beyond that there is no effect. Okay, obviously with time this will change. So if we calculate at a future time step, okay, it may be that this penetration depth or the effect of Ts would have increased. Okay, so it would have increased. It will gradually increase, but still very far away, it still remains initial temperature. So what we're saying is for a 1D problem, if the exposed surface is at x equal to 0, which means here, okay, semi-infinite idealization implies that T remains Ti, which is the initial temperature, as x tends to infinity. So now we can not really neglect the space derivative, but we can now solve the transient heat equation with the following boundary conditions. One is that at x equal to 0, it is the exposure temperature Ts, okay, and at x equal to infinity, which is very far away, it is the initial temperature. These are the two boundary conditions, and an initial condition will be required as earlier, which is at for all x at t equal to 0, Ti is the initial condition. What this idealization allows us to do is that an approximation, an exact solution is possible. Okay. So, the exact solution of Tx T, which is as a function of space and time, we are finding out temperature, it comes out to be in this form, okay, where ERF stands for error function, and this is the definition of the error function. Some of you may notice that this is like a Gaussian curve. Okay, this is how the error function looks like, and most numerical analysis software have already included a function, a built-in function that can give you its value for different values of x. So it is not really necessary to calculate this integral every time. These values are known from a software. It is easy to calculate. So we were discussing this, the distribution here. So this allows us to define something called a thermal penetration depth. So thermal penetration depth delta T implies that beyond a depth x equal to delta, the temperature rise is not substantial, which means for x greater than delta, here temperature is still initial temperature. It does not know that temperature on the other side has increased. And we can define this ratio, that T of x equal to delta comma T minus Ts, which is this temperature, divided by Ti minus Ts. If say this is 0.99, okay, that implies that about 99% of initial temperature and 1% of surface temperature is contributing at this point. Okay. So this penetration depth is an important parameter for say concrete structures, where you may have a section which has reinforcement. Okay, we can find out that whether this clear cover, how much it is in relation to delta. Okay, and that can help us in deciding how much temperature rise has happened or not happened. So I have given a table here where for a relative rise in temperature, we have given delta T expression as a function of time. Okay, so if we are interested in 1% ingress of Ts, this expression can be used, and this is simply derived based on the expression that we have here. So here we put x equal to what we find out x by putting this number as 0.99 or 0.98 or whatever. Okay, so let us look at an example again. Now the surface temperature of a thick concrete wall, which means we can use the semi-infinite idealization, with an initial temperature of 0 degrees suddenly rises to 1000 degrees. Okay. So we are asked what is the 1% thermal penetration depth, which is delta 0.001. Okay. So this is basically this first row from here after 15 minutes, and then what is the temperature T at that point after 60 minutes. The properties are given. Okay. So these are the given parameters. Sorry, this should be 20 degrees Celsius, not 0 degrees Celsius. So to calculate the 1% depth, we know that it is given from this expression, and for particularly for 1% it is 3.6 square root of this. So the 1% depth comes out to be 0.091 meters. So we see it's a very small depth, right? So to calculate the temperature, we define another parameter, which is again, if you see here, delta divided by this 2 square root of it, right? So we get this parameter, and finally we can calculate the temperature. So this temperature is 219 degrees Celsius. So what we see here is that on the boundary, temperature is 1000 degrees Celsius, okay, and at a distance of 0.09 meters, the temperature after 1 hour is only this. Okay, so this is an effect of insulation. So what we have seen so far is to see how to calculate temperatures when outside temperature is constant. However, as we discussed in detail earlier, generally we would want to calculate structural temperatures when they are subjected to the ISO standard fire curve, okay, or the ISO 834 curve. And the reason for this is because most of the fire ratings are derived based on the standard curve. So let us look at an example. So there is a steel beam as shown here, which is exposed from 3 sides. Okay, it is exposed to a standard fire from 3 sides. We want to calculate its temperature as a function of time, and we are saying that initially it was at room temperature. The convective heat coefficient is given, and the nature of the section is also given, ISMB 350. So we find out all the data from basic tables. Right? So these are available from steel tables. Then we calculate section factor. If you recall, we defined section factor earlier, A by V. So section factor comes out to be this. Okay, and the section factor basically, one is A, which is the heat rate parameter. Okay, this is the heat rate parameter, and divided by the volume, which is this. So again, we can solve it using a small code, which becomes handy because then we can do multiple problems of the same kind. So this is the given data. Again, temperature we have converted to Kelvin. These are the material properties, right? So all of them constant for now. So earlier, a flux condition we were using. Now we are given the gas temperature. Okay, so this is the standard ISO gas temperature. Again, this is also converted to Kelvin. Okay, now the heat coefficient. Okay, so that considers now convection plus radiation, where the gas temperature is now time dependent. It is not constant anymore. So again, we do go through the time loop. Okay, rest of the processes remain the same, only that this temperature of gas is getting updated at every time step. Okay, so we do this solution and we solve. This is how the graph looks. The graph in the blue is the ISO standard curve, and this graph in the orange, this is the steel temperature that we have considered. We have calculated rather. So from this graph, you will see that steel temperature almost reaches the standard fire temperature in about 20 minutes. So this is primarily because steel is a very good conductor of heat. So for that reason, most steel members are protected against fire, needs to be protected. So there are generally 4 types of protections which are applied. One is a board protection. So we can use, say, gypsum boards or cement boards for protection. Sometimes there is a concrete encasement which is done. Another very common one is spray applied fire resistant materials. Okay. You may have seen people spraying this and it has a very rough texture on top. The general principle is the same. It tries to protect heat temperature rise or protects against heat flow. And finally, there are these intumescent paints. So they appear like regular paints to begin with. However, when heat is applied, they expand and form a protective layer on the surface, okay, thereby preventing the rise in temperature. So all of these materials will add a thermal resistance between the fire and the steel member. Okay. We have already looked at the concept of thermal resistance. Okay. So thermal resistance is simply defined as conductivity divided by the thickness or the length factor. Okay. So R in is the conductivity. So we can simply use that in our update equation. So earlier this term was not there, but if a protection is there, then this is how the updated equation becomes. So this is the update equation that we can use for temperature calculations of protected members. However, this equation holds true only for materials with small heat storage capacity, which means whatever energy goes in raises their temperature and the storage capacity is really low. But when heat capacity storage is substantial, for example, say in concrete, if that kind of protection is used, then this expression is not accurate. In that case, these expressions can be used. Okay. So how do we decide whether the heat capacity is substantive or not is based on this parameter mu. Okay. If mu is greater than 0.5, then the heat capacity is substantial. And another thing to note is that as mu becomes 0, okay, so this expression becomes that expression, which means storage capacity is not significant. Okay. Eta is an empirical parameter. So for example, for standard fire, eta equal to 5 can be used. Now let us look at an example. So we have a steel column protected by a 30 mm non-combustible board. Okay. So there is a steel column, it is protected on all sides by this board, and we need to calculate temperature as a function of time as earlier. Okay. So again, we have some given data, then we calculate section factor, and then we again go back to the code that we were writing, we just update it a little bit. So here we have shown both the calculations. For unprotected, this part remains the same, there is no change. For protected, okay, so the coefficient changes, where we have this as the original coefficient, and then here d by k, which is Rin, that is what we have added. Okay, so this is Rin, which is the thermal resistance of the member. Okay. So we can calculate and plot. So when we plot, we see here now this blue curve again is the standard fire curve. So this is the fire curve. Unprotected member is this orange, okay, and protected member is in yellow. So we see that the rate of rise of temperature in the protected member is much slower as compared to the other one, which is also as expected. Now we move on to RCC members, which are subjected to the ISO 834 curve. Okay. So for steel members, we saw that the same approach works. Similarly, for RCC members also same approach works. We can still solve the same finite difference equation. Pioneering work was done by Wikström in this regard, who defined specialized formulas when the exposure condition is ISO 834. Okay. So we defined the ratio of Ts to Tf, where Ts is the surface temperature, Tf is the fire temperature. So this is incorporating in some way the convection radiation part. Okay. And then we define Nx, which is Tx by Ts, which is temperature at a depth of x divided by Ts. This in a way is incorporating the conduction part. Okay. We gave a very simple expression like this, where Tx comma T can be simply calculated as Ns times Nx times Tf, where fire is the ISO 834 temperature. Okay. So Ns is defined like this, Nx like this, and then Tf is the fire temperature as earlier. Okay. We can add the initial temperature here, or the room temperature. Now for concrete members, we may also require two-dimensional heat transfer problems. Okay. So these one-dimensional problem that we defined earlier, that would be applicable for slabs or walls, which are say heated from one side only, whereas this 2D heat transfer will be required for beams and columns, which may be heated from two sides, three sides, or four sides also. Okay. So in 2D, again the method is very simple. So Ns and Nx were defined. Now there is an additional thing defined, Ny. So Ny and Nx are very similar in definition, and everything else remains very similar. The expression for Txy like this. So now we do another example. we say there is a 230 thick concrete wall which is subjected to a one-sided fire exposure. Determine the temperature at different depths at 4 hours. Okay. So we have a masonry wall, and then there is a fire on one side, and the temperature of the fire we are saying is the ISO 834. Okay. So from the fire to there will be convective radiative heat transfer, which is taken care of by the factor Ns, and then inside the wall we have factor Nx. Okay, so again we can write a simple code for this. So these are the time intervals up to 4 hours. These are the say locations or depths within the wall at which we want to calculate temperatures. So we are calculating at 1, 5, 10, 15, 20 divided by 1000 because these are in mm. Okay. So now Tx will hold temperature for each x and for each time. Tf is the fire temperature. We have taken room temperature to be 20 degrees. So then we have a loop on x and loop on t, where every time we calculate Ns, which is the factor between fire to surface, and Nx, which is a factor between surface to inside temperature. Okay, and then we calculate Tx. So again, very simple calculation can be automated using codes like this, and then one can plot and see how it looks like. Let's look at one more example of RCC structural members. So we have a rectangular concrete beam, okay, depth and width are given. We want to calculate that after 1 hour fire exposure at 30 mm and 25 mm from the exposed surfaces, what are the temperatures, right? We also want to plot its temperature contours after 1 hour. So we have a concrete beam, okay, and so which means we are looking at 2D heat transfer, and we want to calculate a temperature at 30 and 25 from the exposed surface. So again, given, so x and y is given, so x is on this direction, y is in that direction. So we calculate nx, nx, ny and ns, okay, these are the parameters. Now Tf is the fire temperature, okay, then Txy is using that expression. So eventually what we get is 664 degrees Celsius. So what we are saying here is that this is exposed to a standard fire temperature. So after 1 hour, the temperature at this point is this much. Now we are also interested in drawing a contour to look at the overall heat transfer behavior within the system. Okay. So this is a simple code which can calculate such contours. Basically for contours we need to find temperature at different points in x and y. Okay, we create a grid like that. So that is what is xs and ys is. This is the grid where we want to calculate. And for each x and y, we calculate temperature at each time, and then we look at time t equal to 1 hour. Okay, so this is ns, then nx and ny are inside this, then this is txy, ns times this. Okay, so once we have done that, then we can do a contour plot. Okay, so this line produces this contour plot. So when we look at the contour plot, one of the things I would like to mention is that we have a beam like this which is exposed on 3 sides to fire. Okay, so there will be an axis of symmetry on this. Okay, so this is the axis of symmetry, which means that we can model only the left hand side, I mean only one half of the beam. So that is what we have modeled here. The other side will be a reflection of that. So this side will be a reflection. This only helps in saving some computation time, because otherwise it becomes computationally intensive. So this is how we can draw contours, and you will if you look at say Euro codes or other similar codes, you will see that this kind of temperature contours are given for some predefined geometries. Okay, so to summarize, what we have seen in this lecture is we have seen how to use finite difference method for solving transient heat conduction equation. We have seen it for 1D, but similar logic and principles apply for two-dimensional problems. We have seen a lumped capacity model of heat transfer which can be used for conductive materials like steel, aluminum and other metals. We have seen a semi-infinite idealization which can be used for insulating materials like masonry and concrete. Okay. Then we saw how to do calculations for steel members and for RCC members when they are subjected to the ISO 834 curve. For all of these, we developed simple codes which can be very handy for doing these calculations. Okay. So hope you were able to follow that.